courtesy mode too, by the way. So to find the derivative of y arc secant of x, we're going to do like we've done the other two examples. And so the first step is I'm going to do the composite function. So I'm going to take the secant of y and then take the secant of arc secant of x. Now, cosecant and arcsecant are inverses of each other. They undo each other, and I'm just left with x over here. So then the relationship becomes secant of y equals x. Now, this is important. We found in all of our other examples that we usually at the end will do something with this, okay? Usually. So now I want to take the derivative implicitly, so I'm going to say d dx of everything. So when I do that, we know, or we should know off the top of our head, that the derivative of secant is actually secant tangent. Now, because I am taking the derivative with respect of x of a function of y, I have to tack on dy dx at the end. Now this, the derivative of x is just what? 1. All right. So then dy dx is equal to 1 over secant of y tangent of y. Well, now in the past we've been very lucky. We've just taken whatever this is, right, and plugged in whatever the right-hand side of the equal sign is, which has usually been x. Can't do that this time because of the whole, this tangent thing. Tangent is not cooperating with our plans. So,
is that SEC or SCC?
SEC. It's secant. It's okay. So now what do? Well, what I want to use this. So who remembers what secant is? What's another? 1 over what? 1 over cosine. What's another way I could write tangent?
Secant or sine or cosine.
So cosine of y is the same as 1 over secant of y, and I could say secant of y is 1 over cosine, right? That's one relationship. And then the other thing is that tangent of y is the same as sine of y over cosine of y. So I already know the answer, and I want to ask you guys, what would be nice? I could replace this with an x. But I got to rewrite tangent somehow, some way to use secant. So how do I do that? I'll give you a clue. Think of something that has sine and cosine in it. Some sort of identity. We use it a lot. Well, we're going to make it tangent at some point in time. What identities do we use on the other two examples? Pythagorean one, right? So if I say sine of theta plus cosine of theta, both of those squared, equals 1. How do I make, what do I do to make sine squared of theta equal tangent squared of theta? Well, I divide both sides by well, actually, out to follow the rules of algebra, I have to do it to every term. So if I divide everything by cosecant, or not cosecant, cosine of theta squared, this becomes tangent. Plus 1 equals secant squared of theta, right? That's no accident. Okay? Well, technically the problem's rigged up. So now what do I want to do? I've got to replace tangent with some variation of secant. So what do I do to the Pythagorean identity? How's it written right here?
You gotta solve for secant.
Well, that's going to become x. But what's left? What's the problem? Tangent is the problem. So could I do something like this? Could I say that tangent of theta is equal to plus or minus the square root of secant of theta minus 1? Right? So if I minus 1 to the other side, and then I take the square root of both sides, won't I get this? Yeah? So then I could plug that in here and I'd get some sort of variation, right? I could plug in x's for my secants. In other words, everything will be in terms of secant. So let's rewrite that. So what I've discovered is that tangent of y, dy dx, is 1 over secant of y can be replaced with what? X. Right? Because they mean the same thing. Now, tangent of y could be replaced with plus or minus the square root of secant of y squared minus 1. Right? I'm going kind of slow because I don't want to skip too many steps and have you guys confused. Is everybody good to this point? Now, what I'll do in the next line is I'm going to toss this plus or minus to the front, and I'm going to have x. Now, I want to get rid of all the y's. What is secant of y, really? It's x, isn't it?
Yeah.
So couldn't I say x squared minus 1? Take a second and follow the steps and let that soak in. Okay, good.
Yeah.
So, to recap, here's what we did. We started with the original function y is equal to secant inverse of x. Then we said that dy dx of this function is actually plus or minus 1 over x square root of x. Oh, it's minus 1, not plus 1, minus 1. Right? But now I've got this plus or minus sign in the front. Now here's the interesting thing. This plus or minus business, if I graph the original function, always yields a positive number. Okay? And if you're curious about that proof, it's in your textbook, you can look at it, but really they just look at the graph. It always yields a positive number. How can I guarantee that this always yields a positive number?
X has to be greater than
This will always be positive. And then when you square this x value, that will be positive as well. Okay? So that's the derivative of arc secant of x. Now the reason I went through all that is because that's what example number 3 wants us to do. Example number 3 wants us to take d dx of arc secant of 5x to the 4th. And so to generalize this, I could think of this in terms of u substitution. So if I say y equals secant, arc secant of u, then du dx, or I'm sorry, dy dx is equal to 1 over the absolute value of x times the square root of x, or actually u, because we're going to plug a u in there, minus 1. And then because we have to do some u substitution, we tack on du dx. Okay? So how that works, my notation's a little sloppy. It's kind of hard to read because of, I used the marker. What I would do is I would simply say that this is equal to 1 over, what's u? 5x to the 4th times the square root of 5x to the 4th squared minus 1. And then I've got to tack on the derivative, which is 20x to the 3rd. Is that right? Does that make sense? Does anybody have any questions? So now we've got some nice cancellations that are going to take place. 5 goes into 5 one time, 5 goes into 20 4 times. This squared is 25x to the 8th. So what we end up with is 4 over, oh, we've got 3 x's on the top here, minus 3 on the bottom. So I've got 4 over x times 25x to the 8 minus 1, the square root of all that stuff.
Wait, what's the thing crossed down the top right corner?
This is the derivative of 5x to the 4, which is 20x to the 3rd, right? Does that make sense?
Yep.
Now, ultimately, what we're going to do is I'm going to give you guys a quiz on this. Ultimately, you're going to memorize these relationships. You won't derive those every time. It's much quicker on the test to just memorize those. And like I said, I've got Quizlet flashcards already made with those derivatives. And we'll do a quiz on that in a couple of
It's
days.
just gonna be like matching or something.
Huh?
It's just gonna be like matching or something.
Just matching, yeah. I'll give you the function and to ask you what the derivative is, and then you just have to write this formula. They're real simple. It's like 1 over x squared, 1 over x squared minus 1, 1 over x squared plus 1, 1 over x times the quantity square root of x squared minus 1. So each one has its own thing. Okay? All right. Any questions on example number 3, though?
No.
Okay. Oops, hit the wrong thing.